This is example 10-8, pressure in parallel pipes. So you can see down here, we have water flowing into our little loop at A, and then it splits up, either goes up along B and then to D, or down to C and then into D. And we know that those loops have different lengths, but they do have the same diameter. And we are given the discharge at A, which of course is the same as D, and then we are supposed to find what the pressure drop is between A and D, which of course means that we have to write our energy equation, and then from the energy equation we can get the pressure drop. Now the tricky thing here is that we do not know beforehand how much water goes through B and how much goes through C, right? Because we're not given that information, so we'll need to probably do some iterations, right? Because the velocity of the water going through these pipes is going to impact what the major losses are, and of course those major losses are going to impact what the pressure change is going to be. So we'll have to come up with some iterative strategy. So to do that, we'll want to have a relationship between the velocity in those pipes and the friction coefficients, and then we're going to the friction factors, and then so we are going to choose a set of friction factors and then start there. But to start out, let's figure out how we can get connections between the velocities and the friction factors. So let's maybe start out by just finding the relationship between the two velocities, and of course that will turn to continuity. Right, we know of course that the water that's coming in is at QA. Has to be the same as the water that's flowing out, QD. And maybe we'll just call that Q, right? That's the value that we're given right up there, right? We also know that has to be the same as the amount of water going through B plus the water going past C, right? So we can say that's equal to QB plus QC. All right, so we can solve that for one of the two. Let's solve it for QC. Means QC is Q minus QB. That we can write all those in terms of velocities and areas, right? So we can say VC times AC is equal to Q minus VB times AB. That means VC times pi over 4 DC squared equal to Q minus VB times pi over 4 times DB squared. All right. Now, what can we do? We can solve this for VC. Right, so basically we just have to divide by the rest here. So we said VC would then be multiplying by 4. So 4Q divided by pi divided times DC squared minus pi over 4, they'll cancel it out. So we'd have dB over dC squared times VB. All right, what else can we see? Well, we can notice that dB and dC are the same. So divide them by each other, we'll get 1. So that's just 1. I'll leave the subscript on the dC just to make sure we don't mix it up with dA or dd. So that would be dC squared minus VB. All right, so now we have the relationship between the two velocities. That's a good start. Now what else do we know? Well, we know these are parallel pipes, right? Which means that the head loss along those pipes has to be equal, right? So we can write flow in parallel pipes in parallel pipes. What does that mean? That means that H, L, let's just call them B, and H, L, C have to be the same, right? All right. So we know we can use Darcy-Weisbach to write this out, right? So we can say F B times LB over DB times VB squared over 2G is equal to FC times LC over DC times VC squared over 2G. All right, so we can multiply by 2G, and we can multiply by D, right? Because DB and DC are the same. That means we get FB times LB times VB squared is equal to FC times LC times VC squared. All right, now we know what VC is in terms of VB, so we can put that in. That means FC times LC times what we have up there, so 4 times Q over pi DC squared. Minus VB, otherwise it would be nice and easy. Minus VB, and all that raised to the second power. Okay, that makes that a little bit on the messy side. That means we can say this would be equal to, of course, the FC times LC times the C stays the same, FC times LC. Now times, if we square this, if we FOIL this out, right, so it would be 16 Q squared over pi squared DC to the 4th minus 2 times this times that, so that would be 8Q times VB divided by pi DC squared, and then plus VB squared. All right, so we can, now we have an equation that has FB and FC as unknowns, and then VB, nothing else there, right? So we can, if we now assume values for FC and FB, then we can solve this for VB. So let's write this in the form of a regular equation here. So let's, maybe we'll divide by FC LC first. So we'd have FB times LB divided by FC times LC. Or if we divide everything, all this times VB squared is then equal to 16Q squared over pi squared DC to the 4th minus 8 times Q times VB divided by pi over DC squared plus VB squared. Excellent. So now if we want to gather some terms together and bring them all on the same side, right, then we can say we get something that looks like FB times LB divided by FC times LC. Now if we bring that other one over here, then that would be minus, so just minus 1 times VB squared. Then we have a term here that has a VB in it, so we can bring that over, that'd be plus 8 times Q over pi DC squared times VB, and then we have that one, bring that over, it'd be negative, so 16 Q squared over pi squared DC to the 4th power. All right, this is a nice little quadratic equation that we can now go ahead and solve. Right? To do that, of course, if we want to solve this, we'll have to assume something for FB and FC. So let's say, to get ourselves started, we will assume that FB is equal to 0.03 and the same for FC. All right, that means we can plug all that into our, equal to 0 up here. I'm missing that one. We can plug that into our equation and then we can solve it. So what would that look like? That would look like FB was 0.03. Then the length of LB, says up here, ABD is 8 meters. The other one's 12 meters. Times 8 meters. Divided by 0.03 times 12 meters. Minus 1. Let's not forget that. Minus 1 times VB squared plus 8 times our Q was 0.0215 cubic meters per second divided by pi divided by the diameter. What's the diameter? 50 millimeters. Divided by 0.05 meters squared. Let's see if we can sneak that in here. Oh, no, I don't think we can because we still need to multiply this by VB. So I'll write that, continue down here. So minus 16 times Q squared, so 0.0215 cubic meters per second squared, divided by pi squared, and dc to the fourth, so 0.05 meter to the fourth equal to 0. Now we can throw that into a solver, and that will tell us that the physically correct answer is VB is equal to 6.0280109 meters per second. All right, cool. So now we have VB. If we have VB, then we can go back up here, and of course that gives us VC. So we can say that means VC is then 4 times Q, so 0.0215 cubic meters per second, divided by pi times dc squared, 0.005 meters squared, minus our VB, so 6.0280109 meters per second, which is equal to 4.9218497 meters per second. All right, so what else do we need? Well, once we have our velocities, we can now calculate our Reynolds numbers. Once we have the Reynolds numbers, we can, or independent of that, right, we can find what the what epsilon over d is, and then we can go into our Moody diagram to figure out what our friction factors should be. So let's do Reynolds number at B. All right, just a reminder, rho times VB times, not LB, but dB, divided by mu. Now we're given the temperature of all this. The water is going to be 25 degrees C, so we can go back to our appendix and look up what those values are. So that would be 997.1 kilograms per cubic meters times our velocity, our VB, so 6.0280109 1029 meters per second. Divided by, I already sneaked that in here, times 0.05 meters. And all that divided by, again, something we need to look up, so 8.97 times 10 to the minus 4 Newton seconds per square meter. And that gives us 3.35 times 10 to the 5. All right, so that's our Reynolds number in pipe B. Let's do the same for pipe C. So REC is then, of course, rho times VC times DC divided by mu. Let's see if we can tuck that in a little closer here this time. 997.1 kilogram per cubic meters times 4 times 4.92184979 meters per second times 0.05 meters divided by 8.9, oops, no, let's make this a nicer 997 times 10 to the minus 4 Newton seconds per meter squared. All right, that gives us 2.74 times 10 to the 5 as our Reynolds number. Okay, both of these obviously are well above 2,300, so we're definitely in the turbulent flow regime. So that means we'll have to use our Moody diagram. Now our pipe, what type of pipes do we have? We have galvanized iron. So we go to our Moody diagram and look up galvanized iron. Epsilon is 0.15, right there. So we know galvanized iron, galvanized iron pipe. Epsilon is 0.15 millimeters. That means epsilon over D is 0.15 millimeters divided by 50 millimeters is equal to 0.003. All right, good. So now we have the Reynolds numbers and we have the epsilon over D. So we can go into our Moody diagram, right? So in our Moody diagram, we have our Reynolds number at B was 3.35. So 3.3, that's my blue line right here. 3.35, 10 to the 5, and this one here, my red line is 2.74 times 10 to the 5. Now, some of these are a little hard to distinguish. You can just have to kind of put them in there. And then what do we have? We have 0.03, 0.02 would be here, and 4 is there, so we're not given anything, so we'll just have to eyeball it in the center there. So we go up our red line and go over. That gives us, what do we call this? 0.25, 0.265, I would say. All right, so we can read off that would be, must maybe right here. All right, so we can say from Moody diagram, FB, right? No, FB was the blue one. Doesn't matter. That kind of, we're connecting here. We're connecting there. The blue line is about halfway in between, so FB is equal to 0.0265, and if we do the same halfway point between here and there, right, that would be our C part, we can see that's exactly the same, right? So let's be 0.0265. So FC is the same value. Right, that's kind of because both of these lines get pretty flat in that area already. All right, so now we have our updated values for our F. So we can take those and stick them back into our equations up here, right? So we can go back to this equation, stick it in. We'll get exactly something like this, just with different F values. So if we stick that in, we will get 0.0265 times 8 meters divided by 0.265 times 12 meters minus 1 times VB squared plus 8 times 0.0215 cubic meters per second divided by pi times dc squared times VB, and then minus constant, so 16, if I can write a 6, times 0.0215 cubic meters per second squared now, divided by pi squared times d to the 4th is equal to 0. Right, that's our quadratic equation, so we can solve that. VB is equal to 6.028011029 meters per second. Now you'll notice this is exactly what we got before. Right? Exactly the same value. Why is that the case? Well, if we look at our equation here, right, if our FB and our FC are the same, it doesn't matter what value they are, they're going to cancel out. So that's why we get the same value. What that means is, of course, that our VC is going to be the same as well. All right, so it could be 4.9218479 meters per second. Now these are both the same as previous iteration, so that means we're done, right? So that's officially what we get as our values for the velocities, which now means, now that we've determined what the velocities in both of those pipes are, we can now go ahead and write the energy equation, and then from there get the pressure change. So we can say energy equation where do we write our energy equation? Not that many options, I think. Let's go up here, right? So we'll go energy equation from A to D, because that's where we want to have the pressure drop. A through, nope, not B, but D. A to D. That means we get PA over gamma plus VA squared over 2G plus ZA plus H pump equal to PB over, not PB, but PD. Let's go back there. PD over 2, not over 2 gamma. Now I'm getting ahead of myself. Plus VD squared over 2G plus ZD plus H turbine plus HL. All right, what do we know? It's a horizontal system. What do we know? Horizontal system that means that ZA is equal to ZD is equal to some arbitrary value of Z. We could set this 0, but we can just leave it as Z because it's going to cancel out anyway. We don't have any pumps or turbines. No pump or turbine, which means H pump is equal to H turbine is equal to 0. That's good. What else do we need? So we want to get the pressures, right? That's what we're looking for. We calculated what the velocities are. We figured out what the elevations are. We figured out pump and turbine. Means HL is left. So we can do HL. Of course, we know we can choose either or. Doesn't matter. Let's do B. Right? Because as we said, the losses have to be the same along the two pipes. So we have FB times LB over DB times VB squared over 2G. That is equal to the 0.0265 that we found on the Moody diagram. The length of B was 8 meters. And the diameter is the same everywhere, 0.05 meters. Times the velocity squared, so 6.028011029 meters per second squared, divided by 2 times 9.81 meters per second squared. Right, that's our 2G, and that gives us a total head loss of 7.85262 meters. All right, now we have all the subcomponents, so we can write this, our energy equation again. All right, so again, we're looking for the two pressures, so we'll leave those in. PA over gamma. We know that the velocity at the beginning and at the end are the same. I'm going to write that somewhere up here, just so we have that written somewhere. Same diameter at A and D. That means VA is equal to VD, and we'll just call that V. All right, so if we do that, then we can say we have here V squared over 2G plus the arbitrary Z, no pump, equal to PD over gamma plus V squared over 2G plus Z plus 0 plus HL. All right, so we can of course see that the Z's cancel and the V's cancel. So that means we're left with PA over gamma is equal to PD over gamma plus HL. Now if we bring the PD over, then we can say this would be PA minus PD divided by gamma is HL. That means PA minus PD is equal to gamma times HL. We don't know gamma, but we know rho, so rho times G times HL. And that is, sneak that in here, so that's, if we look up the density, 997.1 kilograms per cubic meters times 9.81 meters per second squared, and then HL we calculated 785,262 meters. That gives me 76,8 810.8 pascals, or 76.8. No, let's make that clear that this is not 768. No, little dot doesn't want to don't want to give a good dot here for some reason. 0.8, there we go, more difficult than expected, kilopascals. All right, so let's go back to our picture. All right, so we found that if we want to have 0.0215 cubic meters per second going through the system, then we'll have to have a pressure differential between A and D of 76.8 kilopascal. And we found that using the energy equation, but first we had to iterate on what the velocities through the two branches are, and we did that by using continuity equation and taking advantage of the fact that the head loss along each of the branches has to be equal.